Alright guys, let's take a look at the solution for the homework for Advanced 2. We had a big laundry list of tasks to complete, and I'm going to go over them one by one using my Git history. Now the first task was pretty simple, just generate a random world of stars, but the stars shouldn't overlap each other. So how do we do this? Well, first let's look at what files have changed. In the commit details, we've got starbro.h, added this guy, and this is just inheriting from entity, and it creates an entity with the star, and it takes an inner radius, and an inner ratio, which is the ratio of the inner to the outer radius, and number of flares, all the usual stuff. And it's got one function to get the radius, and it stores its own radius. So this is kind of interesting. For various operations, we're going to want to know the radius of our model, but when we store our model just as points, it's kind of annoying to have to derive the radius from that. It's possible, it's just annoying. So it's nice to just be able to cache that information when we create the star, and then we can refer to it quickly like this. So we have our starbro. What did I change in vec to? I used the function length squared, but apparently when I copied this over from a different project, it was using a square function that I haven't defined in this project. So I just replaced that with x times x plus y times y. No big deal there. Now in game.h, we include starbro, we include random because, obviously we're going to generate a random star field. And I just do the generation in the constructor of game. And what I've got here is mostly just parameters for the random generation. So, the size of the world, the number of stars that I want to generate, and some parameters about the generation of those stars. So if we go to game.cpp, we see here we're generating our random device or random number generator, and then we're creating a bunch of distributions that we're going to use to generate the different properties and positions of the stars. Now, what I'm using for a lot of these is the normal distribution. The normal distribution likes to clump values around a certain mean value, and they fall off pretty quickly as you go away from that mean. So you're going to have one value, the mean, and most values are going to be close to that, and then you're going to have a range of values that are pretty far away, and then you're going to have a very small amount of values that are on the both extreme sides of the mean. And normal distribution mimics the way that things generally tend to exist in nature, like people's heights. Other things tend to follow a normal distribution in nature. So it takes two parameters, the mean and the deviation, or I forget what it's actually called, sigma, I believe. The sigma, the deviation, is just it's an expression of the amount of variation. So a very low sigma means that most values will be very close to the mean with only a few deviants. Whereas a high sigma will mean you're going to have lots of deviations. It's going to be a broad distribution. So yeah, I create distributions for the position, for the radius and the ratio of inner to outer, number of flares, the color selector, color sampler, and then I just loop while the stars are less than my target number of stars. I generate the radius. I'm using std clamp here to clamp the random generated value to a range, because the thing about the normal distribution is it clumps values around a mean with a distribution, but there is no limit to how low or how high they can go. So if you have a really rare dice roll, you could get a value that is way the hell out there. So I also like to clamp my generated values to some hard range just in case. So that's how I do that for the radius of the star. So I generate the radius and the position, and that gives me enough information to figure out whether that star is going to overlap any other stars in the field. So then I run std any of, and I check to see if any of the existing stars, if the distance from the new star to the existing star is going to be less than the sum of the radiuses. So, if you got two circles, if they're closer to each other than the sum of their radiuses, then they must be overlapping. So if they're overlapping, we just continue on. We don't insert into the container. We generate a new star, position and radius. So we keep doing that. We reject stars that would overlap with other stars. And when we find one that's not overlapping, we generate the rest of its parameters and we put that guy into the container, and that's it. There you go. You've got your random star field. And the rest is just, a lot of bullshit, tweaking these values in here and writing them all out, which was a pain in the butt. That's the pain in the butt. That's what the price you pay for using a normal distribution instead of a what's it called, uniform distribution. But it gives you a more realistic distribution of attributes. Now, one thing I noticed when I was admiring my my little world that I created, my little galaxy, there were gaps between the lines in the polyline models that are being drawn, and that's attributed to the fact that we're using a less than here in the loop instead of a less than or equals to. I mentioned that in the line drawing video, tutorial 1, and I decided to fix that right now, make it a less than or equals, so that no gaps would appear. So that's that, no big deal. Now the next one is I tackled the problem of the in-place transformation. So here, there's a little bit of work to be done. So what I've done is I've made the drawable take a constant reference to a model instead of taking it by value. And then instead of moving, we are going to we're going to take it by constant reference, but we're going to store it by constant pointer. The reason I store it by pointer is because references can't be changed. So that means that if you put a reference in your class, it can't be assigned to. And if it can't be assigned to, then that means that it's going to have a hard time fitting into vectors and other containers. So since it seems a thing like you might want to put into a container at some point, I decided to play it safe and make this a pointer, even though I like references more. So I make it a const pointer. It doesn't actually make any big difference. So then when you store it into the object, you just got to take the address of the model that was passed in, and it will store a pointer to that model. And then once you've captured that, you do your stuff as normal. The drawable passes through the pipeline. It builds up transformations in these member variables. And when it's time to draw, instead of transforming the copy of the model, which we don't have anymore, what I do is I call a function draw closed polyline that takes the translation, the scale x and y, and it will transform those vertices in place. So I pass it a reference to the model, which is going to be a constant reference, because this is constant, right? All right, so then in graphics.h, we obviously add that overload of the function, the one that takes the transformations. And in CPP file, we implement it. So I create a little lambda function here that will transform a vertex by applying the scale in the x and y and applying the translation and returning the result. And then in here, basically all I'm doing is as I'm running through the loop, I am transforming the vertices as I need them. Now, when you draw a polyline, let me just get you a nice picture here. So when you draw a polyline, you're going to start by drawing, let's say, a line from 0 to 1, right? So you got to transform 0 and you got to transform 1. Then you draw a line from 1 to 2, so you got to transform 1 again and you got to transform 2. So if you just do the naive approach, do a loop, transform both every time, you're going to be transforming each vertex twice when you only really need to transform it once. So a little bit of a semi-micro optimization to do here is to remember, where did I put it? Current. So I do a vec2 current, and that remembers the current vertex. So we start with 0. So 0 is the current, and then all we got to do is transform the next one, draw from current to next, and then overwrite current with next, and then it leapfrogs. So the next thing, you've got your current, which is now 1. You transform number 2, you draw it, and then you put the transform value of 2 into current, replacing 1, and you keep going until the end. And then in the front and the back, you need to draw from current to front, which I also cache because you need that to connect to the back. But there you go. So here I'm drawing them all. I'm doing it in place, and I am not duplicating any of the work of transforming a single vertex. Very nice, not too complicated, beautiful. Next task is culling all the stars that are outside of the camera's viewport. So in order to do this, we need a few things. So the basic idea is we got some scene. Our camera is in the scene, and it controls the region of the scene that is currently going to be rendered. So we can represent that with a rectangle in the world space. Each star can be roughly represented with a box that completely encloses the star. We call this, we usually call these aligned axis bounding boxes, because their sides are all aligned to either the X or the Y axis, and they bound the star. No part of the star exists outside of the box. So basically what we want to do is we want to check to see if our viewing rectangle overlaps a star. If it overlaps, that means that that star has a chance of being drawn. If it doesn't overlap the star, we know that that star has no chance of being drawn, so we can just reject it immediately. So in order to do this, we need to be able to calculate our viewing rectangle, and we need to be able to calculate the bounding boxes of each of our stars. So obviously a good first step is to add a rectangle class to our little simulation here. And this I just pulled from, I believe I pulled this one from Fartanoid, because that's where we used it for the most gainful employment. So we pull rectf into this project. For our star bro, I just do a function get bounding rectangle, which will get us the bounding rectangle based on the radius. So the radius, and this is one of the reasons why I made star bro and made it store the radius, because we wanted to use that later to get the bounding rectangle. So that's very simple. For camera, bounding rectangle may be a little more complicated. I call it the viewport. So what you've got to do is you have to account for the amount of zoom or the amount of scaling. So when you zoom in on the world, you scale objects up, but you're also scaling the rectangle down. So you're making the rectangle smaller in the world, thus making the objects that appear in it relatively larger in the viewport. So to calculate the zoom factor, which is the scaling on the viewport, it's the inverse of the scaling that is being applied to the objects in the world. And after that, it's pretty simple. We just generate a rectangle from center. We use the position of the camera, and we use the screen width, half the screen width, because this form center takes a half width and a half height. So half the screen width multiplied by the zoom factor, and that's it. Generate your rectangle. And once you got that, it's a simple step. Outside of the loop, we get the viewport rectangle, because that doesn't change between stars. And then for each star, we check if star.getBoundingRect is overlapping with viewport. Gotta love this syntax, right? Very nice. All right, the next task was to make the stars animated, to animate their color and to animate their size, their scale. So how we do this? Well, let's start with the color here. Star color pulsing. So obviously animation is going to give us an element of time into our game, so I've decided to add the frame timer into the project from somewhere else. And let's take a look here. Entity.h. So I added a function to set its color, because that was not available up until now. And in Starbro, I've added a bunch more parameters here to control the animation. So the way I do the animation is, let's see here. I use sine wave, and this is pretty common. If someone tells you you need some kind of rhythmic motion, some kind of harmonic motion, you're looking at sine and cos. You can do it. You could have, like, let's say you just didn't know about the existence of sine and cos, was something super foreign to you. You could have done it with a simple, for loop type deal, or not really a for loop, but a variable that goes up and down. We did that in beginner once, and that would give you a sawtooth wave. But sine wave is actually simple, does it in a single function, and it's a smoother It's a smoother function, so it can look nicer. The general way that I implemented the glowing is if you looked at my animation, you could see that stars generally had primary colors and they would glow to white. And how you do that is, well, if you've got R, G, B, let's say you've got green, so your star is green color. So G is going to be 255, R and B are going to be 0, and if you want to glow that to white, you want to raise your R and B up to 255 while keeping G at 255. So the way I do that is I add, every frame, I add a certain offset value. So I might add, let's say in a given frame, I might add 100 to each of the components. So R and G will be at 100, green will be at 355. Then I clamp them all down to 255. And there you have your color, which is going to be a light green. So as the frames, proceed, this value gets higher and higher. And so does this one. But they all get clamped to 255. And the way I do that is the value that is being added, I set that to 127 plus, and to that value, I add a sine wave that has been scaled so that its peaks are, about 127, 128. And when you add those together, you get something like this. So you get a sine wave that peaks from about 255, and the troughs are at about 0. And that is what I add to all RGB, clamp to 255, and that gives me my glowy shits. Now, you also, for a sine wave, you also want to control the frequency, the squiggliness of the line, and the phase, which is, how much, let me just show you. So let's say you got a sine wave, looks something like this. If you change the phase, you're basically just sliding it around on the x-axis like this. So, if you have, let's say you've got two sine waves and they have the exact same frequency, if they have the same phase, they will be moving in complete they'll be synchronized. But if you put them out of phase, then, when one is going brighter, one might be going dimmer or whatever. So I just like to randomize the phases. But since the frequencies are also randomized, it's not that important to randomize the phases because they're probably not going to sync up anyways. So anyways, that's that. Scale it by 127 or whatever, and you multiply by some frequency factor and some color phase, and you add 128. That's the offset that I showed you there in the diagram, and there you go. And then we add those to RGB, and we're clamping that to a maximum of 255. So we take the minimum value between whatever we've calculated and 255. There you go. Then you set your color. That's update color. Not that complicated if you understand how sine trigonometry works to a certain degree. If not, maybe a little more complicated. Maybe you had to use some kind of variable that you increased or decreased every frame to create a saw wave. But either way, it can be done. Oh yeah, and in game.h, obviously I add parameters for that stuff. And in game.cpp, I've got to add extra distributions and, generate those parameters in here, pass them into this constructor. Down here, I got to get the delta time, and I've got to update all the stars now in the update model, because now they do something every frame that is dependent on time. And there you go. And then for the radius, it's pretty much the same deal, right? You're going to have an amplitude. So basically here, what the sine wave is generating is it is generating a scaling factor that you're going to multiply with. It's going to be based around 1. So it's going to be, if this is 1 on the axis, the scaling factor is going to look something like this. So it's going to be, at certain times, it's going to be scaling the star smaller than its normal size, other times larger. Never scale down to 0, and there's a hard maximum as well. And I generate this range here, this amplitude, again, randomly with a normal distribution, also with the frequency, also with the phase. So lots of parameters to generate. Parameters are stored in here. Call update scale in the update function, And down here, we just scaling factor is equal to amplitude times sine, frequency, and then we scale it by 1 plus the factor, because our sine wave is centered around 1 here. And of course, this means a whole buttload more parameters to mess around with, and in game.cpp, more stuff to generate and pass into our constructor. And if you do that, you've got scaling. Well, you've got throbbing anyways. And if you do that, it looks something like this, but there's a problem. Maybe you guys can anticipate it. Let's try and scale off the screen now. I've got this star is extending up to this point here. So I'm going to put my mouse pointer on the point that it extends to, and I'm going to scroll down, and you can see if I scroll down to a certain point, star no longer appears on the screen, even though it should still be extending up to here. So it should be visible, but it's not. Why is it? Why is it that it immediately disappears at a certain point here? Well, we are doing our culling, and we are culling based on our radius. But our radius is just the radius that was remembered when we created the star. Radius is now changing, so we've got to take that into account when we do our culling. So how do we do that? Well, actually, I lied. There's two problems. One problem is that now stars can actually overlap each other because they grow, right? So although we are generating our random star field so that they don't overlap, we're only accounting for their base size, not their expanded size. So in order to account for their expanding size, I do a function called it getMaxRadius, and that just returns radius times 1 plus the radius factor amplitude, which is the maximum that the sine wave is going to generate. And this will get us the max radius, and this will generate the stars so that they can no longer overlap even when they're all at their maximum size. So that's one thing you need to do. Then you need to also account for the animation in the culling. So what you do here is a very simple change. In getRadius, we just return radius times the return value of getScale, the current scale of the star. And that's all you need to do, because if you look at getBoundingRect, I made it so that it doesn't refer to radius, but it refers to getRadius. And this is a smart thing to do in your code. Instead of, if you've got a choice of inside of a member function, you could use the getter, or you could directly access the member variable. And you might think, I'll just directly access it. And I often do this myself. But it's actually smarter to use the getter, because then later on, if the conditions change and you have to refactor, say if you have to take into account scaling when you're getting the radius, by using getters in places like this, now, when I have to refactor and change, all I got to do is change the implementation of this one function that encapsulates this property, and everything just falls into place afterwards. Again, it's the beauty of using encapsulation properly. And you put all those pieces together, and you've got a beautiful world. We've generated a whole new world for us to explore and marvel at our creation. Lovely. So I hope you guys enjoyed this video. I hope you guys enjoyed the homework. I thought it would be a nice palate cleanser after all that straight math from the tutorial 1 homework. But I don't know, let me know what you guys think, if you like this kind of homework better or whatever. And I'm going to see you soon with some more C++.